All right, good afternoon. Welcome to this week's CFA Colloquium. And it's a pleasure to introduce our speaker, Suvy Gezari. Suvy did her master's degree, got her master's degree at UCLA, from UCLA, and then moved to Columbia, where she got a PhD in 2005. She then moved on to Caltech as a postdoc and spent a couple of years at Caltech, and then was a Hubble Fellow at Johns Hopkins before she moved to University of Maryland in 2012 as an assistant professor. During her time at both Caltech and Johns Hopkins and now at Maryland, Suvy has worked on a wide range of topics in time domain astronomy using primarily GALEX, which she will tell us about things that she will tell us about today. But over the last few years has also been a very important member of the Pan-STARRS key project on variables and transients, where she's done a lot of work with our group here at the CFA. So without further ado, I'll turn things over to Suvy, and she's going to tell us today about tidal disruption events, or how supermassive black holes kill stars.
Yes, so whenever you have a press release, you need something dramatic and exciting. And so this was our press release tagline, and it did get a lot of attention. Supermassive black hole caught red-handed in a stellar homicide. In fact, I was interviewed by the Baltimore local news, and when we were prepping for the interview, I said, you know, could we do a transition like, speaking of homicide? But no, we did not. He did not like that idea. It's too sensitive a topic. So yes, it's wonderful to be here at Harvard CFA because, of course, I've been working with a lot of you. Some of you have already moved on from Harvard now, but there are many people here that have been active members of this Pan-STARRS Science Consortium. And so I have many collaborators who are now or formerly at Harvard. And of course, I've been doing a lot of work with the GALEX space mission. So in my talk, I'm going to tell you all the exciting things that I think we can potentially learn from tidal disruption events. I'm going to show you the excellent progress we've made in the past decade in particular on detecting candidates across the electromagnetic spectrum. In particular, I'm going to focus on how we've searched under the lamppost by taking advantage of the wide field and high cadence of the GALEX time domain survey in the UV and the Pan-STARRS medium deep survey in the optical to search for these events. And then I'm going to focus on one excellent example in which we had enough evidence from this crime scene, otherwise known as observations, where we could determine the victim, which in this case is a star, and the perpetrator, which is a hungry black hole. And then I'll conclude with what really is the promising future for detecting large numbers of these tidal disruption events, but some comments on how we can prepare ourselves and make this process more successful. So usually when we talk about tidal disruption events, we like to start with this schematic diagram from Rees's Nature paper in 1988, where he shows you what was realized by theorists to be an inevitable consequence of a supermassive black hole lurking in the center of a galaxy. And that is that if a star approaches close enough, namely within this tidal disruption radius, the tidal forces of the black hole will overcome the self-gravity of the star, rip it apart, and some fraction of the stellar gas will remain bound to the black hole and be available to accrete, likely producing a luminous flare of radiation, and then some fraction of the debris being ejected at high velocities. So this was our picture in the late 1980s. However, thanks to Enrico Ramirez, thanks to Enrico Ramirez Ruiz and his former student James Guilachon, who's now a fellow here at Harvard and unfortunately is not in the audience to defend himself, they have really stepped up the quality of simulating exactly how the material in a tidal disruption event rains down on the black hole as a function of time, and these are now detailed hydrodynamical simulations. But interestingly enough, even when you do all this beautiful detailed physics, we get a pretty simple picture about what happens when you tidally disrupt a star. And basically, as a consequence of the Keplerian fallback of the material to the black hole as a function of time, you get this simple characteristic t to the minus 5/3 power law decay. Another really interesting thing about tidal disruption events is that their timing is very sensitive to the mass of the central black hole. And of course, as astronomers, we love weighing black holes, especially potentially in distant galaxies. And so this is a really unique probe of black holes, in particular dormant black holes, which are very difficult to study. So in fact, the rise time to peak, or the time at which the fallback rate peaks since disruption, scales the black hole mass to the 1/2 power. So as you increase the black hole mass, the time scale increases, as well as the peak mass accretion rate decreases. But interestingly enough, I also show here the Eddington limits corresponding to those mass accretion rates. And you also expect different accretion behavior depending on the mass of the black hole, namely that large black holes should be mostly sub-Eddington accretion, but the smaller black holes may in fact go through a large portion of their decay during a super Eddington regime. So this is an interesting insight on accretion physics. Okay, so what can we learn from TDEs? This is now my sophisticated diagram of a tidal disruption event. And of course, I just argued that we can potentially weigh black holes in the centers of galaxies based on this characteristic timing of the fallback of material onto the black hole. There's a neat consequence of the fact that the tidal disruption radius scales with the black hole mass to the 1/3 power, whereas the Schwarzschild radius scales the black hole mass linearly, such that as you get to bigger black hole masses, you get to a point where the Schwarzschild radius actually becomes larger than your tidal disruption radius. So for above 10 to the 8 solar masses, solar-type stars are actually swallowed whole before being disrupted. However, due to, we know from general relativity that if you have a maximally spinning black hole, you can shrink your event horizon you can shrink your event horizon and therefore actually increase the maximum mass that can disrupt a star. So if you saw a tidal disruption event around a greater than 10 to the 8 solar mass black hole, and you think it was a solar-type star, you could pretty clearly say that the black hole must have been spinning. Okay. We can also probe the types of stars that are getting swallowed by these black holes, and that's again because the fallback rate of material, and in particular the tidal disruption radius at which a star is disrupted, depends on the mass and radius of the star. And it turns out that it also depends, the fallback rate also depends on the internal structure of the star. So there actually can be an imprint of the radial structure of the star on this fallback rate as a function of time. So we can potentially measure or probe the mass and radii, radial profiles, and maybe even the chemical composition of these tidally disrupted stars. What's both interesting and problematic is that in order to successfully model and interpret these events, we have to understand the accretion physics going on. And in particular, what's exciting is the physics of a newly formed accretion disk. So a lot of what Enrico's group is doing is trying to take these beautiful simulations, which are showing you how this material is starting to build up around the black hole, and maybe taking the next step and trying to figure out how does that material actually accrete and radiate. A recent really exciting discovery from the SWIFT mission was that in fact not only do tidal disruption events produce these newly formed accretion disks from the stellar debris, but as we know in astrophysics, accretion and jets often come hand in hand. So it's not surprising that we now have a new class of tidal disruption events in which we're not seeing a flare of accretion onto the black hole, but we're actually seeing a newly formed jet on axis in the line of sight. So tidal disruption events might tell us some clues in general what it takes to form jets in accreting supermassive black hole systems. In addition, of course, these black holes are swallowing stars. We have to get the stars into the tidal disruption radius around the black hole, and that's due to scattering processes in the nucleus of the galaxy, and so it's very sensitive to the orbital distribution of the stars in the center, and of course, as well as the stellar population. So the rates of tidal disruption events give us a window on the nuclear stellar populations in galaxies. In addition to stars around black holes in the center of a galaxy, there's also going to be gas. And so we can potentially probe the circumnuclear environment of a black hole that was previously inactive by either photoionizing this gas with the accretion flare from the tidal disruption event, or as Ido Berger studied in detail, looking at the interaction with a newly formed jet with circumnuclear material. So what I really like about tidal disruption events is this idea that we can actually probe the demographics of supermassive black holes and even probe some more exotic scenarios which supermassive black hole aficionados enjoy discussing. For example, potentially detecting a recoiling supermassive black hole that happens to be tidally disrupting a star. It turns out that the rates of events are very sensitive to the presence of a binary supermassive black hole system. You could potentially disrupt white dwarfs around intermediate mass black holes, which would be a signature of such small black holes in dwarf galaxies. And again, you could look for signatures of spinning supermassive black holes from looking for events in more massive, around more massive black holes. So once we probe these black holes, we can always then connect them to their host galaxies. And what's really nice about tidal disruption events is they're particularly sensitive to this lower mass black hole range, where these nice relationships between black hole mass and host galaxy properties like velocity dispersion are less well constrained. So it's an interesting mass range to probe with a new method. So tidal disruption events are amazing, and let's go find some. So first, what are we looking for? Well, based on some sort of simple assumptions of this fallback of material onto the black hole, which then accretes, you expect sort of a burst and power law decline of thermal radiation, and you expect it to have, if you just look at the characteristic temperature of a disk radiating at around the Schwarzschild radius up to around the tidal disruption radius, that corresponds to temperatures of about 10 to the 5th to 10 to the 6th Kelvin. So it's basically the typical temperatures of the inner regions of an accretion disk. And so you expect that to peak in the extreme UV and soft X-ray. And in particular, we would really like to find a tidal disruption event in an inactive galaxy so that we can really say that before this event, the black hole was completely quiescent and starved of fuel, and suddenly we had this dumping of material due to the tidal disruption of a star. Because as we know, a ubiquitous property of active galactic nuclei is in fact variability. So we're a little wary about being able to differentiate between large amplitude AGN variability and this more dramatic, impulsive process. So unfortunately, the rate at which stars come close enough to be disrupted is quite low within a galaxy, so maybe once every 1,000 to 100,000 years. But we're now at the point where we have surveys at various wavelengths that are imaging galaxies, millions of galaxies in multiple epochs. And so we now are surveying enough galaxies that we can be lucky enough to catch these events in the act. So in fact, in the last 2 decades, and in particular in the last decade, we've really gone now from a handful to over 24 tidal disruption event candidates, and they've actually been detected all across the electromagnetic spectrum. I've been focusing mostly on the UV and optical, which I will discuss in a second. But shown here is sort of a timeline of tidal disruption event discoveries. The first, when they were reported, The first handful of candidates were from the ROSAT All-Sky Survey. And then when I started my postdoc at Caltech in 2005, I started searching for these events in the UV and optical, and there have been several more candidates have emerged from archival studies in the X-rays, but there's been a lot of momentum now in the UV and optical in the last few years. If you notice in this diagram, which is a diagram of peak luminosity versus publication year, there are two sources here which really stand out. These are the SWIFT hard X-ray selected tidal disruption event candidates. And in this case, they have super highly Eddington luminosities, and they do not look like a thermal spectra. And in this case, these events look like they're actually due to jetted emission in your line of sight. And so these are a completely different beast, but very exciting for trying to understand jets in jet formation and tidal disruption events. But I'm going to be focusing on this more classical thermal emission that we associate with the sudden accretion of the debris onto the black hole through this debris disk. So as I said, the first candidates were from the ROSAT All-Sky Survey. There have been several more from things like the XMM Newton Slew Survey and archival searches in Chandra. And these sources are very convincing in that they have high luminosities, large amplitudes. They have extremely soft X-ray spectra, which are really hard to, very different compared to an AGN spectrum. And their rates are consistent with what you'd expect for tidal disruption events. And if you place, these are all the ROSAT flares, if you place all their points together, in general, they're consistent with this t to the minus 5/3 parallel law decline. But these are very sparse light curves. Basically, at best, you have sampling of a few years in these events. So my goal was, even though the emission from these events should be peaking in the soft X-rays, unfortunately, we don't have an all-sky soft X-ray survey to work with right now. So why don't we search under the lamppost and take advantage of these beautiful, especially optical supernova surveys which have daily cadence and high sensitivity in wide areas, so that we could actually get detailed light curves of tidal disruption events and try to do all the things that I motivated in my other slides, namely try to get enough information that we could actually probe the black hole mass, the mass and radius of the star, its polytropic exponent, and even the spin of the black hole. So let's look under the lamppost, and also with using these wide field time domain surveys, enable prompt multi-wavelength follow-up so that maybe we can capture that high energy emission in follow-up observations. So the first proof of concept for this was searches that we did with GALEX that happened to overlap with the CFH-TLS Supernova Legacy Survey, as well as searches in purely optical data with the Sloan Stripe 82 survey. And in these cases, we detected, we sort of went out looking for nuclear flares. With the GALEX data, it wasn't necessarily nuclear because the spatial resolution isn't as good, but we were just looking for large amplitude flares. And what's really interesting is the optical sources are shown here, the optically selected sources. These two sources here were selected based on their UV properties, but yet their optical light curves that we extracted after the fact from the overlapping optical data look very similar to the optically selected candidates. And basically, these look like blue transients that follow this t to the minus 5/3 power law decay. So this was sort of proof of concept that we could study these high energy sources at longer wavelengths. Note here that we don't have any constraint for these sources on the rise time of the events, which is one of the most critical diagnostics for black hole mass. So there was more work to be done. So while we're starting to get some nice light curves, we really want to catch these things on the rise to use them to weigh black holes. So again, I wanted to use the GALEX satellite because of its wide field of view and its UV sensitivity. But I wanted, instead of studying galaxy evolution and the star formation rate history of the universe, I wanted to use this telescope to study high energy transients in the time domain. And to do this, we also wanted to team up with Pan-STARRS, which is a beautiful wide field optical time domain survey, in particular the Pan-STARRS Medium Deep Survey, which has about 10 7 square degree fields that it visits every night as it cycles through 4 bands, GRIZ, and then Y bands during bright time. So we took these 2 telescopes, and they're actually very well matched in terms of their per epoch sensitivity as well as their field of view. And we matched the cadence, we designed the cadence of Galax to be complementary to Pan-STARRS. And so we get this nice I guess we call it now co-observing between Galax and Pan-STARRS. And so any source could then be studied, any transient source could be studied both in the UV and optical without worrying about your decisions on follow-up. So shown here are just the Pan-STARRS fields that we monitored with Galax. Galax are the blue circles, and Pan-STARRS is the green circle. And these are famous extragalactic legacy fields. So the UV is actually a very exciting place to look in the time domain because it's relatively unexplored compared to the optical, X-ray, and gamma ray. And there are lots of science drivers for why you should care about the UV transient universe. I talked at lunch about this exciting potential to detect core collapse supernovae very early after explosion. We think that we know that tidal disruption events should be intrinsically very bright in the UV for months to years. But it also turns out that active galactic nuclei are very UV bright, as well as have larger variability at UV wavelengths. And variable stars also show larger variability at UV wavelengths. So here's now just the temporal overlap between the 2 surveys. And when we analyze all of this multi-epoch near UV imaging, we find that the UV universe is mostly made up of AGNs and quasars. Here I'm just differentiating which look like point sources in the optical and which have an extended galaxy in the optical. But we're really dominated by accreting variable supermassive black holes. We also detect some variable stars, including M dwarfs, R Lyrae, and some CVs. But what's exciting is we have this gray slice here of extragalactic transients, which don't fall into necessarily the category of AGNs or supernovae. And so these are where we are kind of looking for these potentially large amplitude nuclear flares from quiescent galaxies associated with the tidal disruption event. So one of our most extreme, or the most extreme extragalactic transient was in fact this one here, which showed over 4 magnitudes of variability in the near UV. And this is compared to all the quasars and AGNs in our survey. So they also have large amplitudes of variability, but on a different level than this source. So this plot is really indicating that this looks like it's a true transient source in the UV. It's not just a fluctuation of ongoing behavior. It was also detected very clearly in optical difference imaging by the Pan-STARRS Medium Deep Survey. And so when we took a spectrum of this with the MMT telescope, thanks to a collaboration with Ido Berger and Ryan Chornock here at Harvard, it was interesting because some experienced spectroscopists looked at this and said, oh, it's just a quasar. That's just magnesium-2 at redshift 0.96. So now, in retrospect, we should have said, well, even if it's a quasar, that kind of behavior is unlike any quasar we've ever seen. So who cares if it's a quasar? It's still interesting. Turns out it was not a quasar because we actually had to wait until late time spectra. So luckily, Ryan Chornock knew that it would, and we had detected with Galax, so we knew it was interesting, but we were smart enough at least to keep following it, even though we thought maybe it was a quasar. And over time, the continuum emission from the transient faded away, which initially was very blue, and eventually we got to see the calcium HK absorption features from the underlying galaxy, indicating that this was in fact a galaxy at a redshift of 0.17, an early type galaxy, and that broad isolated feature was in fact helium-2 4686, which is actually a high ionization line that had been originally predicted to be possibly associated with tidal disruption events because it requires soft X-ray photons. So now we had the redshift and from the host galaxy luminosity. So here's the before, it's not detected in the UV. Here's the after. Here you see the host galaxy and the blue transient on the galaxy. Based on the luminosity of the galaxy, the black hole mass in the center of this galaxy should be around a few million solar masses, which is safely in the range of a black hole that can disrupt a solar type star, and it has a low star formation rate. And now here is the beautiful pan-stars and GALEX light curve. So the pan-stars data with its beautiful 3-day cadence really captures now the rise and decay of the light curve, and this is a logarithmic scale in time. And you see the rise to the peak, and you see that what's really striking is that the UV emission remains very bright over a year after the peak. And so if any of you study supernovae, or you'll know that sure we can detect supernovae in the UV at early times, but they always expand and cool, and the UV emission drops extremely rapidly on the timescale of days. So this long-lived UV emission and this beautiful rise and decay was really striking. So we can take this beautiful light curve and fit, which were at the time were the best models, numerical models for the fallback rate in a tidal disruption event. And I haven't done any translation here between accretion rate and luminosity. I've simply said that the luminosity in each band just follows the accretion rate. And you get a remarkable agreement between the shape of the light curve in detail and this simple calculation of what the fallback rate, the Keplerian fallback rate as a function of time is for a tidal disruption event. So you can use then the rise time of this event to actually weigh the perpetrator here, the black hole, and determine that the black hole mass is 2 million solar masses, but you still have an uncertainty here related to the mass and radius of the star disrupted. What's really neat is recently, or last cycle, we applied for HST follow-up with the idea that while the source has faded away, is probably faded away to below the limits of certainly ground-based imaging, in the UV, in principle, we should still be able to detect this event now over 4 years after the detection. And so just by extrapolating just a t to the minus 5/3 power law here, very simple, you can predict, given the range of models, what you'd expect to see with HST. And so we just observed it in June, and in fact, it's continuing to decline in this simple power law fashion. And what's really fun is that while in the optical, which is the gray and black contours, the grayscale and black contours, while in the optical it looks like a galaxy, in the UV it's a point source. So the magenta is the UV image. So it's, right now in the UV all you're seeing is this fading tidal disruption event, and it's still shining. And we can use the beautiful astrometry or the spatial resolution of HST to really pinpoint and confirm that this source is in fact nuclear. We're going to start approaching some of the systematic errors in determining what is the nucleus of a galaxy, but we can certainly continue to strengthen this idea that this really is a nuclear accretion event onto the black hole. So it took us a while to identify these helium-2 lines, and there's a reason for that, which is that you don't normally see a spectrum with only helium-2 emission lines. You would also expect to see bomber line emission. And so we can measure the velocity of this line, and it's pretty broad, about 9,000 kilometers per second. And given the lack of H-alpha detected, we get a ratio of about greater than 5 helium-2 to H-alpha. So if you use standard emission line diagnostics, that would indicate that your hydrogen mass fraction in the gas is very low. Okay, so our idea was that, okay, these lines are telling us about this disrupted star, and in fact we're seeing high velocity debris from the star that was disrupted, and that this star that was disrupted was hydrogen poor. It was actually helium-rich. So potentially we're seeing here the victim in the crime scene. We're seeing this high velocity ionized helium gas indicating the type of star was disrupted. So that's when we could really put our black hole behind bars, because if we assume that this was in fact a helium-rich star, based on the lack of star formation in the host galaxy, and the timing of the event, we rule out an evolved star like a massive Wolf-Rayet star, which has lost its hydrogen due to winds. We think that in fact this could be the core of a red giant star that was stripped by this same black hole. So it's stripped of its hydrogen at earlier times, and now we're seeing the disruption of the helium-rich core. And we can measure the luminosity of the event, the total energy, how much mass, a lower limit to how much mass was accreted. And based on what we think the structure of a stripped red giant is, we can plug in the mass and radius of the core of a stripped red giant, and then pinpoint the black hole mass even further to 3 million times the mass of the sun. So the idea is that in this event, not only did we have this beautiful light curve to get the timing of the event, but we actually knew about the structure and chemical composition of the star disrupted, so we could actually model the black hole mass. So I'll say that it's hard to put error bars on a mass like this, because it really depends on your assumptions for the star disrupted, and it's also model dependent in that so far I've been using these mass accretion rates curves to predict the timing of a flare, but of course what we observe is the radiated luminosity. So Guillechan et al. Tried to take their mass accretion rate curves, but then look at the structure and emissivity of the disk producing the emission, and try to actually model the radiated flux, and then see how that evolved with a function of time. And so what's really problematic in this source is that given its low temperature and the fact that with a declining luminosity you would expect a declining temperature, you would expect band effects, and that in the UV and optical band you would expect a different power law decline if your bolometric luminosity was tracing the mass accretion rate. So they have a really hard time fitting this light curve when they use sort of a realistic disk-like spectrum for what they think the accreting debris disk should look like. And so in order to get the model to fit the data, they basically have to make it such that the specific luminosity in the UV optical band basically follows the mass accretion rate. And they do that using a reprocessing layer, and I'll talk about that in a second. There's also possibilities, another way to explain the low effective temperature of this emission. So we've fit a black body temperature of 30,000 degrees Kelvin. Another way that this has been accounted for is another paper which thought that maybe it was a very low viscosity disk, and that produced a lower temperature. And then there's also this other factor in that some of the luminosity is coming from the viscous evolution of the disk, and some is actually coming from the accretion process. So this is all going to change how you relate your model, your light curve fits to the actual black hole mass. So what is the nature of the continuum emission in these tidal disruption events that we're detecting? So all of our events are share similar characteristics, and they seem to show this hot thermal emission, and they do show this nice power law decline in behavior, but their temperatures are actually a lot lower than what you'd naively expect from an accreting debris disk. So shown in this diagram are the peak bolometric luminosities of the events versus their black body temperatures. And you also see here a selection effect in that the optical events that we detect are biased to lower temperatures, and the X-ray events that we detect are biased to higher temperatures. If these things were really black bodies emitting at a fixed radius, then they should follow these diagonal lines on the luminosity temperature plane. And shown in the dashed red lines are the Schwarzschild radius of a 10 to the 6 to a 10 to the 7 solar mass black hole. And the gold lines are the radii of the tidal disruption radius of a 10 to the 7 solar mass black hole, 10 times the tidal disruption radius, and 100 times the tidal disruption radius. So basically, from theory, you might expect that you're going to see this accreting debris disk with emission coming from maybe as small as the Schwarzschild radius and maybe as far as maybe twice the tidal disruption radius. And that's going to give you temperatures that should scale with luminosity in this rectangle here. So we certainly do not see that. What we do see is that the UV and optical candidates seem to be telling us that the radiation is coming from larger radii. We also appear to have a constant temperature. We both observe fixed colors with time, but we also don't see this shallower decline that you would expect if the temperature of the emission were changing as the luminosity were declining. We still see this T to the minus 5/3 power law decline. The X-ray candidates have the opposite problem. They appear to have uncomfortably small radii, some even smaller than the Schwarzschild radius, and so perhaps they're probing more something like an accreting hotspot in the inner regions of the debris disk. So there is some old work by Avi Loeb and Ulmer in 1997 thinking if there were some sort of envelope of debris that could reprocess this high energy emission from a tidal disruption event, that would be really fortunate because the temperatures and luminosities would be much better for optical surveys to detect. So in fact, that seems to be the case. We seem to be finding this type of emission in our candidates. So the question is that what's going on? Is there some sort of reprocessing layer? The only issue with the reprocessing layer is that it has to have a sort of a complex behavior in that it has to regulate itself such that it has to shrink in just the right way for the temperature to remain constant. So basically, if the luminosity is declining as T to the minus 5/3, you need the radius to be declining as T to the minus 5/6 so that you end up getting a constant temperature. But there might be physical ways in which the radius of the photosphere could be changing due to opacity, and I think James and Enrico were starting to investigate that in their paper. So is our object PS110JH the archetype? So it turns out that the Palomar Transient Factory went back into their archives of all of their transient detections, and they ended up finding several or 3 nuclear flares, one of which in particular had a striking resemblance to PS110JH, both in its light curve. So the open circles are our object, and the solid circles are from the Palomar Transient Factory object. And they have, I don't think there's any scaling here. I think they just literally pasted them on top of each other. But you can see that the rise, the shape of this initial peak, as well as even the late time decline, is very similar to our event. But not only are they similar photometrically, but they are also similar spectroscopically in that this object, which has the nicest light curve, also appeared to have broad helium emission and no corresponding H-alpha emission. And they have two other objects. They don't have as nice light curve sampling, but they do have spectra for their other two objects. There was also another tidal disruption event candidate reported in a nearby galaxy, which had a very nice late time light curve sampling. And what they found is that there seems to be a spectrum of spectroscopic signatures from these tidal disruption event candidates. So all of these were selected from optical surveys, but it looks like they show, either they show only broad helium emission, or some show both hydrogen and helium emission. And so this is exciting because this is potentially, we're seeing gas, we're actually tracing now the kinematics and ionization state and chemical composition of the gas in these tidal disruption events. So there's a lot of information here. So the question is, what is the origin of these broad lines? Originally in the literature, people focused a lot on line emission that could come from the unbound debris intercepting the accretion flare. But I think this line emission was expected to be quite weak, and Enrico and James, I think, emphasized in this paper that in fact the cross-section of this stream is very narrow, and so you actually would have very weak or unlikely catch in the line of sight emission from that unbound debris. So they propose, in fact, that the line emission is coming from this newly formed accreting debris disk that somehow circularizes and starts feeding the black hole. And then so then the question is, are we seeing, so let's say these broad lines are coming from this accreting debris. Why do some only show helium emission? Where is the hydrogen emission line? Hydrogen emission in these objects. So either it's because the disrupted star itself is hydrogen poor, or the alternative explanation is that it's due to the ionization state of the gas, and you're sort of looking at the inner regions of what you could think of as like a truncated normal AGN disk. And if these conditions would just suppress the hydrogen emission so that you would get an enhanced helium to hydrogen ratio. So there was a recent paper by Gaskell running cloudy and using sort of a truncated broadline region cloud and trying to get as high a helium to H-alpha ratio as possible. And what they found was that you could get a ratio of about up to 4, but only at a certain critical density of about 10 to the 11 per cubic centimeter. So we can pretty stringently measure the amount of H-alpha both at peak in our spectrum, as well as we now have some nice late time spectra. The late time spectra are nice because now we're just seeing the host galaxy light, so we can improve our subtractions to isolate the emission from the transient. And we're pretty sure that our helium-2 to H-alpha ratio during peak is greater than 5, and we still don't see any H-alpha popping up in this late time spectrum. However, we always have to be close to our observers because it turns out that rest frame H-alpha happens to land in a telluric line, so we're trying to be very careful. Ryan Chornock is being very careful in his reduction of this spectrum. So one of the predictions of the Guillochon paper is that as this debris disk expands with time, so shown here is their model with this is ionizing photons, flux versus density. And as this disk expands with time, the densities fall and you start to get into a regime, a more normal regime seen in other AGNs, where you would have a stronger H-alpha to helium ratio. So the red line is showing where our September 2012 spectrum lands in their models. And at that point, just according to this plot, this isn't a model, this is a set of models from an AGN paper that they used. But based on where that red line lies, you would expect an H-alpha to helium ratio of greater than 3. So you would actually expect H-alpha to be stronger than helium-2. And we can, I think that would actually be detectable in our spectrum if that wasn't in fact the case. So it seems that we don't see the H-alpha line popping up as you would expect in this explanation. Also, we still have to understand why these PTF tidal disruption events, which also had spectra at early times, why do they show hydrogen when you would expect at early times for the hydrogen to be weak? So this is a very exciting area, and there's a lot to be learned from the spectroscopy of tidal disruption events in real time. So I think we're entering the era of precision tidal disruption event observations, where in precision I mean we're going from light curves with a time sampling of years to a time sampling of days. And the next great tidal disruption event factory is really going to be LSST, because of its major increase in survey volume. And by scaling the detection rates in our study with the Sloan survey, you would expect that a survey like Pan-STARRS would maybe get a couple events per year, which isn't maybe a factor of a few off of what we observed. But something like LSST is going to detect thousands of tidal disruption events per year. But if we're going to find thousands of tidal disruption events, we're going to find millions of supernovae, which is great for some of you in the audience, but not good for me. And so the question is, how in the world are we going to sift through all of these transients to find our really exciting tidal disruption events, so that we can then go take our spectrographs and go take our other follow-up instruments to study them in detail and study their central black holes? So with the Sloan study, we found a parameter space where these tidal disruption events did stick out from supernovae in particular, and that was in the color evolution with time versus their color. So basically, tidal disruption events have constant colors with time and are intrinsically very blue. So they are hot, and unlike a supernova which expands and cools, tidal disruption events seem to have relatively constant temperature. So you can use this parameter space to really rule out most supernovae. You can also look at the host galaxy colors to look at where tidal disruption event hosts appear to be redder than, of course, the star-forming like galaxies of hosts to core collapse supernovae. So we've started trying to do this with Pan-STARRS. So Sloan had the U-band, and LSST will have the U-band. In Pan-STARRS, we did not have the U-band, but we did have these beautiful, deep light curves of many optical transients. And my graduate student, Sid Kumar, went through and wanted to classify all of the extragalactic transients, so any transient with a galaxy host, and went through and did some very intensive light curve fitting to decide. We basically made the hypothesis that the extragalactic universe is made up of two types of transients, AGN and supernovae. So it turns out there are other exciting things in there like tidal disruption events, but that was our main hypothesis, that either you have bursting transient sources or you have stochastically varying sources. And so he did light curve fitting to determine, is something stochastically variable or is it burst-like? Then with the next step we said was, okay, what is its offset with the host galaxy? We made the other basic assumption is that anything that's nuclear and stochastically variable is probably an AGN. Anything off nuclear that is a bursting light curve is also probably a supernova. It's probably associated with an exploding star. But then there's some other off-diagonal terms. For example, a nuclear source that is a bursting light curve, certainly it could be a supernova because supernovae can go off near the centers of galaxies, but it could also be a tidal disruption event, which is what we're looking for. So we use this combination of general light curve class and offset, and we can do some fun things like look at all of our photometrically identified AGN and supernovae and look at some of their basic properties. For example, host magnitude, or the difference between the transient magnitude and its host. And you get this neat relationship that the AGN and supernovae kind of lie in different parts of these parameter spaces. And so instead of spending the hours of crunching through all of these light curves, at the telescope with just a couple of measurements, for example, with an LSST transient alert, if all you had was the host magnitude in the I band and its transient detection in the I band, you could give it some probability of whether it was an AGN or a supernova. So if the transient was very bright compared to its host, you're pretty sure it's got to be a supernova. Whereas if it's in this regime where it's close in magnitude or fainter in magnitude than its host, then it's harder to differentiate between supernovae and AGN. So we can take all of these photometric classifications and kind of look at this space again of color decay versus color. And this is very busy. This is what it's like for me every day, looking for something interesting. This is what you have to deal with. So you stare at this, and you stare at light curves. And in here are amazingly exciting objects, but there are also boring ones too. And what's neat is that, in fact, the supernovae, of course, do stick out in this quadrant here. They're redder, and they evolve quickly with time. They cool quickly with time. You'll notice that there are purple circles here. These are nuclear transients, so we couldn't decide if they were an AGN. We couldn't decide if they were a supernova or a tidal disruption event, so we just call them nuclear transients. But probably if they're in this box, they are supernovae. The yellow highlighted are supernovae that have been followed up mostly from the Harvard supernova pan-STARRS program. So you see that what we say are supernovae are in fact supernovae when you observe them spectroscopically. But then you have this sea here of bluer objects with less color evolution and are bluer. And the two stars are the two spectroscopically confirmed tidal disruption events from pan-STARRS. And so while they are in there, and maybe there aren't that many nuclear transients around them, so maybe there's a manageable number, it's still a little bit daunting how much potential contamination there are from supernovae and AGNs. And so what if we then put on our near UV goggles, and we could figure out which of these sea of transients actually had bright UV emission, were also bright UV variable sources. And suddenly things get a little quieter, which I guess, that's sad in that you have less sources, but you know that these sources, a lot of them are really interesting. So the UV preferentially picks up mostly the AGNs and quasars. The quasars are the blue dots. AGNs are the green circles. The UV does pick up a few supernovae, which is always exciting because supernovae are only bright in the UV at early times. And so at the lunch talk, I talked about at least one of these supernovae where we actually caught the rise of the supernova in the UV. And so it is very exciting when you see a supernova in the UV, but there are very few of them that actually get detected because they only last for a short period of time. And it also depends on the type of star exploding. But what's exciting is here you have our two tidal disruption events, and now the confusion from other sort of nuclear transients has really quieted down, and there are only a few sources left in this color space that could potentially stick out as tidal disruption event candidates. And a couple of them that, I don't know if you can tell, are in yellow, we have spectra of, and it looks like they're in fact AGN. And we could also look at another view like their host colors, and you can see that the tidal disruption event hosts are much redder than a lot of the other hosts, and so that could be another important discriminator. So my main point of this is that while the optical transient universe is exciting and active, it's also very confusing, and it really helps to have another perspective on transients, especially if you're trying to find high energy events like tidal disruption events. It really helps to have that high energy information. So what is the future? I'm sure there are definitely people in this room who want a space mission at higher energies to complement LSST. And shown here are all European missions. This is just a proposal, a UV proposal. eRosita is going to launch in 2016. But for that to actually complement LSST, you'd have to extend its baseline mission. And then there are some ideas for a hard X-ray all-sky telescope, which would be very sensitive to these relativistic tidal disruption events, these jetted events where the emission is non-thermal. But really, we need, these are all European missions, we really need a NASA mission so that we're ready for LSST to be able to capture the most exciting energetic events. So to summarize, tidal disruption events are potentially a relatively clean laboratory to study black hole mass and the nuclear stellar populations in galaxies and potentially black hole spin. They're very important tests of accretion physics, meaning that we have to understand the accretion physics for us to be able to model them properly. And they can also tell us about jet formation and black hole environment. I showed you one example where we think we actually caught a black hole red-handed in a stellar homicide, whatever that means. And the future really is promising for detecting more of these events, but we have to be smart in how we find them, and having a high energy mission like GALEX or ROSAT would be extremely powerful. Thanks.
Thank you, Suvy. We have time for some questions. Avi.
As you know, one of the big problems in the theory that has not been resolved over the past 2 decades is how the stream that is produced intersects itself and eventually leads to the formation of an accretion disk. Is it conceivable that there are lots of events that we don't see because the intersection doesn't take place? In other words, that there's only a subset of all the disruptions?
Absolutely.
Okay.
Yeah, I mean,
the rate that you find.
It's remarkable that we see events that show this simple t to the minus 5/3 behavior. I mean, it doesn't make any sense that it would follow so cleanly, because like you said, that's the fallback rate. That is not the actual accretion rate onto the black hole, because you're assuming it's that the viscous time is very short and somehow the material is accreting at that rate. But it's shocking, and it really does look that simple. So, but certainly, yeah, if there was some sort of time delay, for example, between the disruption, fallback, and formation of the disk, but for some reason the accretion rate on the disk had that same parallel behavior, observationally we can't probe that time delay unless something like Enrico has worked on the possibility that at the time the star is disrupted, you have some compression that could form a shock that could produce a burst of X-ray radiation. So potentially you could actually time the time of disruption, but that's very faint and difficult to detect.
So you use methods to weigh the black hole, and you said that if you find some that are greater than 10 to the 8 solar masses, you can infer that it's spinning. But does the fact that it's spinning make your methods for weighing the black hole any less reliable, or is that not an issue?
So there have been calculations for the fallback rate, so taking these curves and predicting them in the case of a spinning black hole. And there are some changes in the timing of the event, but the actual shape doesn't change. So I think there could be some subtle changes in the timing of the curve, but it would probably be on a smaller order than the fact that the time scale that you measure is so long that it must be a very big black hole.
I could imagine that early in the universe, all of the stars that were easily going to be eaten got eaten. And then you have a situation like the Milky Way where you have a lot of stars basically in orbit around the black hole. And they're going to be perturbed perhaps only a very little bit by the slight granularity in the gravitational potential. And so I'm wondering, perhaps almost all of the impact parameters might actually just be marginal to give you only a little bit of tidal disruption. And the star might even survive another couple orbits and be tidally disrupted increasingly as time went on. But perhaps most of these events are with impact parameters that are very, very marginal for getting actual disruption of the star.
Yeah, and Enrico's group explored that parameter space and found that there was a large range of impact parameters in which the core of the star remains intact. And there also have been some papers thinking about, like you said, multiple passages and some sort of periodic signature from the accretion of the star. But yeah, certainly the rates depend on how often stars are scattered into the lost cone.
I was surprised when you showed those color blindness tests.
Yeah, yes.
What you call those confusion diagrams. That you didn't use the time history. It seems to me the tidal disruption event only happens once, whereas an AGN flare
So
can
that's
happen more than
how
once.
I made the shapes. So I defined, so nuclear transient means that it had a bursting shape.
But only once.
Only once, exactly.
Ah.
Anything stochastically variable that was in a galaxy nucleus, I called an AGN. A stochastically variable source off-center from a galaxy nucleus would show up here probably as a gray circle. And that could be a recoiling supermassive black hole, but before you get excited, it could just be bad astrometry. So this is all of these classifications are photometric, and they take into account the light curve shape and the offset from the host galaxy.
But what about the long-term history? You have 5 years of pan-stars data.
Exactly,
So the
so-
AGNs come back a lot.
Exactly. So anything
Oh, we can throw those
I
out.
call an AGN is specifically modeled with a damp random walk,
Yeah.
stochastic
Okay.
ongoing.
Okay. So it isn't as bad as you make it look here. You know
This,
those
but
are not.
I know what these are, and it's still a headache. I know that all of these are bursting transients, but they
Yeah.
could be supernovae or they could be
Yeah, I
tidal
got it.
disruption.
I got it. I just
Yeah.
ignore the green ones. That's
Yeah, ignore the green. Yeah, green, you're right. It's not that bad.
good.
Take
I
away
can't
the
tell the
green.
difference anymore.
The purple is what we're after. The
Yeah, I
purple.
got it.
Enrico?
Yeah, I think very nice. Like I wanted to comment a little bit on the hydrogen and helium issue, because I think it's quite important. So I think the point that we're trying to make is these are AGN that are made from the inner parts to the outer parts. Yeah, so the disk basically starts from the inner parts and expands. And if you take a broad line region of an AGN, because of reverberation mapping and also looking at the width of the lines, you know that basically the higher ionization lines are very deep in, and as you go outside, they're the lower ionization lines. So the prediction is that initially, everything will be highly ionized, you won't see it, and then you go from the high ionization to the low ionization state. Now, you're absolutely right that we really have to understand in detail the structure of the reprocessing layer, and assuming maybe that it's the scaling laws of the broadline region are very similar, you may be incorrect, because here you have this elliptical disk that is not perfectly spherical expanding. But then if you really want to go into the other regime, which is, okay, I'm going to assume that the star is a helium star, particularly at those masses, just the rate of pure helium stars is tiny. And even if you have a red supergiant and you want to strip the hydrogen, what we show is that you cannot strip as much as hydrogen as that remaining in the core, because these red giants tend to, rather than expand by losing mass, they start contracting at some point, and it's very, very difficult to do it. So I tend to believe that we know the IMF of galactic nuclei relatively well, and we don't, and now we have like 40% of all the tidal disruptions being helium stars. I tend to prefer the other reasoning, which their main sequence, and what we're seeing is the changing in this reprocessing.
Unless the environment that these stars are in are extreme. I mean, now we have this G2 cloud star.
Sure, but imagine, for example, the life story of a red giant. So you will have to go and strip its envelope, and then change its periastron, its pericenter distance significantly to disrupt the core. And the probability of that is minuscule compared to the tidal disruption.
So that is for the theorists to wrestle about. There's a paper. Yeah, okay. Oh, sorry, but
Well, at least the two that are in this room.
There's a paper that goes through the dynamics, Bogdanovich et al., and they say that as long as you have to accrete all that hydrogen gas that got stripped, but they do have some orbital solutions where you could get the core subsequently disrupted. But my argument against the hydrogen to helium ratio is that it's just so hard to suppress the hydrogen enough, and Gaskell barely did it with sort of standard cloudy calculations. So even if the hydrogen is ionized, you're still going to get recombination, and I think it's just really hard to get such an extreme ratio. So until I see a calculation that does it,
we'll show you the radiation transport calculation.
Okay.
I think it's not as crazy.
So then why are these guys at early times showing hydrogen?
That's an interesting question.
Okay.
So,
So if,
this discussion needs to happen on a longer time. So
Yeah.
Charles, you have a question?
Well, you did
Yeah.
actually just barely mention G2.
yeah.
So isn't there a useful analogy there for you?
Wait, so
Real time?
G2, this is sort of hot off the presses, and I'm not on the groups working on it, but now the idea is that G2 isn't just a simple gas cloud, but G2 might be it does have an interior star that's still intact, but it has gas that's being stripped off and out of layers. But we still have to explain this bizarre dusty envelope around the star. So in the Gez's group's paper, they suggested it could be a stellar merger. So that's fun. Stellar mergers are rare, but it could be that in the environment around a supermassive black hole, that's not crazy. So back in the day, Kobayashi et al., I think 2004, predicted that you should see a population of helium stars from stripped red giants in the centers of galaxies. So I'm fine with either explanation. I wouldn't say just because they're rare. I think it's still interesting because these are extreme environments. But I also just know from the spectra of AGNs over time and even supernovae, it's just very hard to suppress the hydrogen emission. So if you can do it, then we have to understand, how you do it, and then how you get the different scenarios. But yeah, more observations, the better. More over time.
Yeah.
Higher
What Ido
sequence
pointed
noise.
out to us is that you do see the trend that things that peak at very early times, which means that the disk hasn't developed as much, so no hydrogen and helium. Things that peak slightly later show, basically the helium, and there are these things that basically show some hydrogen that, in fact, if you look at this standard scaling laws of AGN, they're very far off the hydrogen, emission line. So, or argument there is maybe you have a residual disk, before the tidal disruption, and you have enough gas at lower densities to give you the hydrogen, but
Okay.
I think it's interesting that we're seeing a broadline region form in real time.
Absolutely.
And I think it's
And
very
yeah.
exciting to try to understand what are the properties of those.
Definitely, and actually modeling your line ratios as a function of time is extremely exciting. And we, as observers, we need to give you more spectra to model.
Great, so we all have our work cut out for us. So let's thank Suvy again for that.